Alright, so let's take a look at this problem. This problem is 8.9 out of our textbook, and it reads, the figure below shows or provides steady-state operating data for a solar power plant that operates on a Rankine cycle with refrigerant 134A. So this would be like an organic Rankine cycle, and because you're using a refrigerant that has carbon in it, so like refrigerant 134A. Okay. So that's the working fluid, and they label states 1, state 2, state 3, and state 4. So as it goes through the solar collector, it's like going through a steam generator. It's picking up heat, and they have this symbol, the Q dot in per unit area. So that's the solar load on the face of the solar panel. Not all of it's absorbed. They're going to talk later about a percent efficiency. They'll have a 60% solar input into the collector absorbed by the refrigerant as it passes through. So this Q dot in or on the face of the solar collector per unit area is due to the solar radiation, and it's 0.8 kilowatts per meter squared, and 60% of that's striking this face actually gets into the refrigerant, is absorbed by the refrigerant. Okay, so from 1 to 2 you go through the turbine, we understand that. From 2 to 3 you go through the condenser, you're rejecting heat, and right away we have a little complexity coming out of thermo 1, because it's like if I have a little control volume, that's what they're showing right here for this turbine, then W dot T is positive out of that turbine. Great. But when we come down here, we have a little control volume around the condenser, and then they have this symbol Q dot, and it's Q dot out. And if you think about it, normally if you don't have any out on it, you just say Q dot. Oh, that would be in, positive in. And then, so you're always struggling with a sign problem here to keep these things straight. So here it's like Q dot is shown as positive in the outward direction. So, okay. Go to the pump, the same thing. You have W dot pump is positive going into the pump control volume, which is opposite of our thermo 1 sort of sign convention. All right. Well, let's go ahead and finish reading the problem. It says, determine the solar collector surface area in units of meters squared per kilowatt of power developed by the plant. So this plant has some W dot out of the plant, let's say net out of the plant. And you want that to be, I don't know, maybe, I don't know, let's say 10 kilowatts. I'm just throwing out a number. You would need to find out how big this is, so that if somebody said, no, now we want the plant to be 20 kilowatts, what do you have to do to the size of the solar collector? Well, this is a factor of 2 increase. You would increase the solar collector size by 2. But we need to find that ratio. So what we're asked to find is a little different than what we're accustomed to. It would be the area per W dot net. That's what we're asked to find. So this would have units of meters squared per kilowatt. Kind of a funny unit there. So how are we going to solve for it? Well, take a look at all the information given. We're given a table, which is nice, where we have the state 1, 2, 3, 4. We have the pressures, and the key information is this enthalpy column, and then also the quality. But the key information really is the enthalpies here. So if we go around and we construct, it's like they've given us a table of the properties. What we want to do is get another table. I think it's helpful to organize our information in a table, in a summary of the energy transfers for each component. So if I come over here, I'm going to say, well, how many components do I have? Well, I have a turbine, then I have a condenser, then I have a pump, and then I'm going to have this, I'm going to call it solar collector, okay? And we can have a Q or a W for each of those. A heat in transfer in units like kilojoules per kilogram. Here, because if the mass flow rate through the turbines the same as through the condenser, through the pump, through the solar collector, it's a lot easier. Later we'll have it where the fluid streams split and go to different components and a little more complex, but here you can just put everything per kilogram. So it's per kilogram that goes through the turbine, which is the same as per kilogram that goes through each of the other components. Likewise, kilojoules per kilogram for that work. Now, you look at the turbine, and the standard assumption about the turbine is that it's well insulated. You look at the problem statement, it says the turbine and the pump operate adiabatically. So yeah, there it is. But even if they didn't say it, you would look for information and probably have to make that assumption that it's adiabatic. So the pump, no heat transfer. The turbine, no heat transfer with the surroundings. All right. Then you'll also look and think about this condenser. It has no work transfer, no shaft in or out. Likewise, that steam generator or solar collector, 0. So half of this table is 0, and now we can populate the other half of the table. If we do a first law for this work or this power out of the turbine, it's equal to the mass flow rate through the turbine times the enthalpy coming in at state 1 minus enthalpy going out at state 2. Hence, the lowercase w of that turbine, which is cap W dot divided by M dot, is just equal to the enthalpy change H1 minus H2. So that's what you have to do for each of these components. Likewise, well, let me finish out for the value here for that turbine. You have the H1, and then you subtract the H2, and then you get the work that the turbine produces per kilogram going through the turbine, 20 kilojoules per kilogram. Go to the condenser. So we have, let me do it slowly here, Q dot out is equal to the mass flow rate going through the condenser, and it comes in at high enthalpy, goes out at low enthalpy. And so the lowercase q for the condenser is equal to the H2 minus H3. We're given the H2. We're given the H3. So Q of that condenser is 172.32. And at this point, because I'm going to sum all of these, and so we'll get the net, I want to think about reverting back to the sign convention, because really this is a heat rejection right there. The work for the pump, and you can say, well, here's the two enthalpies for the pump. It comes in a lower enthalpy, goes out at a higher enthalpy. So what is that? It's 1.77. But again, that's the positive into the pump. If I want to do a sum on this column, I'll put a negative there so that the W net is 18.23. That's really what I want. I want that W net. That tells me for every kilogram that goes through the solar collector, through the turbine, through the condenser, through the pump, we get a net workout of 18.23 kilojoules. So that's the key piece of information. We can come over here to that solar collector, and we just have this enthalpy coming in, the enthalpy going out. So there's a gain of 190.55. Leave it as a positive, a gain. Do the sum in this column, so we can find that we get the 18.23. And at this point, you compare the two, and they're good. They're the same, the 4 significant digits, and so life is good. It's all okay. So Q net's equal to W net for this system. Okay, what I'm going to need to do is scroll down and get more space to continue solving this problem. So I'll go ahead and do that. So there's a couple of equations that you want to play with. Like, let's say you want to know the Q dot that gets into the refrigerant. Well, how would I calculate the rate of heat transfer that's coming into the refrigerant, well, you would say, how big is my solar collector? And then you would have, what is the load, the solar load, I'm going to put SOLAR, on it per unit area, because that's really what was given in our problem statement. And then we multiply by an efficiency for that solar collector. Hopefully that equation makes sense. So if we have a larger area, then we're going to get more, higher rate of heat transfer into the refrigerant as it passes through that solar collector. So the area, then Q dot solar divided by the area, that was given in our problem. That is the 0.8, just so that you emphasize that. That was given to be 0.8 kilowatts per meter squared. And then the efficiency, we'll leave it in symbols, but it's 60% was our efficiency. Okay. Now, once we have that Q dot into the system, we can say, well, what is my W dot net out of the cycle, the power that's being developed, the net power out? Well, isn't it going to be proportional to the Q dot that gets into the refrigerant, and multiply that by the cycle thermal efficiency? Sure, that makes sense. Well, at this point, we now can calculate that cycle thermal efficiency. Let me run it over here. The cycle thermal efficiency is, we're going to be able to get out 18.23 kilojoules of net work per every kilogram going in the loop. But what's provided is what comes in this solar collector, 190.55. So our cycle thermal efficiency comes in at a whopping 0.09567, a little less than 10%. So that's what it is. So it's like we got this right here, and this one comes down from there. I mean, you can expand out the equation, you can kind of see where we're going. This is equal to the cycle thermal efficiency times that area times the Q dot solar per unit area times the efficiency. I wrote it a different way, didn't I? Let me do it. Well, great. Just call this efficiency of the solar collector. So we have efficiency, thermal efficiency of the plant, and the efficiency of the solar collector. Well, now we can see how to get the answer that we want. We want the area divided by the W dot power. So if I rearrange this equation, I'll have the area divided by W dot net is equal to the 1 over the thermal efficiency, Q dot solar over the area, and then the solar collector efficiency. So let's plug in some numbers. This is 0.09567 dimensionless. This is our 0.8 kilowatts per meter squared. This is our 0.60, and you get that we get 21.776 meters squared of solar collector area needed per kilowatt of net power out of the plant. And that's our answer. If I was on an exam, I would go ahead and put it somewhere like this, rewrite it. W.net is equal to 21, and I would round off the three significant digits, 21.8 meters squared per kilowatt, and box it. And if it was part A, I'd put part A right here, something like that. If the answer for part B, put B. But let's just stop right there and let's scroll back up. And yep, that's the answer that we were looking to calculate. Now let's solve this problem. So this is problem 819. We have steam. Steam is H2O, it's water, is the working fluid in an ideal reheat cycle shown in the figure. Okay, what does ideal mean in this context? Well, typically that means any pump or turbine efficiency is 100%. Isentropic efficiency of a turbine or a pump is 100%. And now we have a reheat. Well, what do you mean by reheat? Well, you pass it let me just try and sketch what a reheat cycle looks like. You have a steam generator, and you're going through for a first pass, and you put it into a first turbine stage, turbine 1. And then as you come out, maybe what you do is you take some of that or all that steam back to get it reheated, and then continue it in the second turbine stage, then go to a condenser, and then after the condenser go to a pump, then from a pump go back in the loop. So that's our reheat. So you pass it through, then you reheat it. This is the reheat right here. So you'll have some heat added, and then you'll have some heat added in the reheat as well. Okay. The mass flow rate is given to be 1.3, so m dot is equal to 1.3 kilograms of steam per second. That's flowing through the first pass of steam generator, through the first turbine stage, through the reheat, through the second turbine stage, condenser, and pump, etc. And they give us an illustration right over here. It's a temperature entropy diagram. Here's our dome, steam dome. So this is the top. That'd be our critical point. All these are saturated vapor. All these states are saturated liquid, and they put states on. So state 1 is right here coming out of the steam generator before the first turbine stage. State 2 is after. State 3 is after the reheat. State 4 is after that second turbine stage. State 5, it comes out saturated liquid at state 5, that's after the condenser. You put it through the pump, puts it up in the compressed liquid state, state 6. And then you go from saturated liquid at that high pressure and you heat it. When it's heated in that steam generator, there's a phase where it's heating the compressed liquid to get it up to be at high enough temperature so that it starts to change phase or boil. And then there's a phase change from saturated liquid all the way to saturated vapor, and then it continues and is heated to be superheat, and that's up in the superheated steam region at state 1. Okay, so what is the power developed by the cycle in kilowatts? And they give the answer right here, but here are information in our states, which is nice. And so we do the same thing. What we need to do is, since we already have a table of the properties, you want to get a table of the energy transfers for each component. That's what I recommend. And that helps with the bookkeeping and find our errors. So I would just say, how many components do I have? And then what is my Q, kilojoule per kilogram? And then what is my work in kilojoule per kilogram for each component? And so I can start with maybe the first turbine 1, go to the reheat. Do not forget the reheat. Easy to forget the reheat. And then the second turbine, and then the condenser, and then the pump, and then the first pass through the steam generator. And I didn't leave quite enough room, because what I'm going to do is I'm going to sum each of these columns and get a net. Then I'm going to make sure that Q net is equal to W net for that cycle. If they're not, then I look for an error. Okay, so you just kind of walk through this. What do we have for the first turbine? Well, put in the numbers that are 0 first. It's adiabatic. Well, where did they tell us it's adiabatic in this problem? Well, it's a standard assumption that there's no heat transfer. And if you go to an actual power plant, they actually wrap these turbines in some sort of blanket, insulating blanket, and then when they need to service them, they take that blanket off. I mean, that blanket's maybe I don't know, 5, 6, 8 inches thick, so it's pretty good insulation. All right, then you have the reheat. That has some no work in the reheat, but you have heat transfer. Turbine, second turbine, no heat transfer, but yes work. Condenser, no work, but yes heat transfer. Pump, no heat transfer. And then steam generator, no work. And so I maybe should have tried to draw some lines going across to help keep those straight. All right. You say, well, what is that work of the turbine? Well, it's a change in the enthalpy. And so it comes in at high enthalpy and goes out at low enthalpy. You take the difference in those two enthalpies, and you find that it's 642 kilojoules of work out of the turbine, which means out of the system, per kilogram of steam flowing through the turbine. You go to the second turbine stage, and it's going from 3 down to 4, so the enthalpy difference here, and that comes in at 643. All right. Then we take a look at the pump. The pump is boosting from 5 to 6, and so from 5 to 6 there's enthalpy gain. That magnitude of the enthalpy gain is 14.5, but when I put it in this table, because I want to sum, I'm going to put a negative sign there. That way when I do the net work, it's like, okay, that has to be fed back into the cycle. It detracts from the net power out, and we get that it's 1270.5 for QNet. Okay, let's go and do for the reheat. So the reheat is between states 2 and state 3, right in here, this reheating. So heat's coming from the surroundings, burning some fuel, something like that. So from 2 to 3, you have an increase in enthalpy. And when you calculate the increase, it's 422 kilojoules per kilogram. Go to the condenser. This one's going to be a heat rejection. First, I calculate the magnitude of the heat rejection. So it comes in at state 4, goes out. So you do the difference. That's 2257.1. And I could still talk about that's the positive magnitude of heat rejection out of the condenser, but because I'm going to sum this column, I'm going to put a negative sign right there because it really is a heat rejection or heat transfer out of the system. And then I look at that steam generator. It's going from 6 all the way up to 1. That's an addition. That addition is 3105.6. And I do leave that positive. So it's like positive heat addition in the reheat, positive heat addition as that first pass through that steam generator. And then when we do the sum of this column, it needs to match 1270.5. And if these don't match, if they're not the same, we have an error somewhere, and no sense proceeding. Find our error. So since they match, we're good. This is great. So now we have a table of our energy transfers, table of our properties to help us get that table of energy transfers. Now we can solve for part A. What is that power developed by the cycle? I need to scoot down just a little bit. So we say, well, what is our power developed by the cycle? Well, W dot net out of the cycle would be the mass flow rate through the cycle times the lowercase w net. Okay, well, our mass flow rate was given to 1.3 kilograms per second. Again, that's right here, 1.3 kilograms per second. And then we have our 1,270.5 kilojoules of work out for every kilogram flowing. So our kilograms cancel. We have our kilowatts. And so our W dot net comes in for this problem at 1652 kilowatts. I compare matches to 4 significant digits. A lot of times it doesn't, but this time it does, that's great. We're happy. All right. Then what is that plant thermal efficiency? Well, let me scroll down a little bit more. So the thermal efficiency of the plant would be what I desire. I need a lot of work out per what I have to provide into the plant, and that's my heat transfers in. So it would be this W net divided by, and I have two places where I have to add heat. I have to add heat, the burnt fuel, to add heat and the reheat, and then also in that first pass in the steam generator. All right. So using these numbers, we have 1270.5 kilojoules per kilogram net work out, and then for the reheat 422, and then for the steam generator first pass 3105.6, and we calculate the thermal efficiency. It comes in around the 36.02%. 36.02%. And then we can scroll back up and see how that compares. Yeah, it compares well. So those are the two problems I want to solve today. And at this point, I'm going to go ahead and stop this lecture.